Okay, so good afternoon. I think we start now. Yeah. Now already 3:20. Yeah. Okay. So for the discussion just now, any question you want to ask? Yes. No, you're not here. Okay. So if no, what? Okay. Okay. So if no, I think we continue as we discuss the p value, yeah, as I promised just now. Okay. So you see the p value, yeah. So because actually in for us, yeah, for us we should use p value more frequent, yeah, compared to the critical value. So we continue with the example just now. Okay, make sure you yeah, of course most of you have the taken the notes. Okay, so the same diagram, yeah. So this is 1.96. This is 1.645. This is 1.82. Yeah, 1.82. Yeah. So we have this. Right. Okay. So now we see the this again, this area. Yeah, this area actually representing 2.5%. Remember, okay, 2.5%, the purple color. Okay, the purple color. Okay. So we see, of course, we should actually use two sides. Yeah, therefore we get 5%. But we say 2.5%, we only use one tier, therefore 2.5%. Okay. Now, now you see this value 1.82. So therefore, we cannot. Okay, the conclusion is that cannot reject. You cannot reject the null hypothesis. Okay, so because the test statistics 1.82, 1.82 is larger than, is smaller. Yeah, smaller than the critical value 1.96. Okay, so therefore at 5% level, we cannot reject the null hypothesis. Yeah, this is the test statistics. Now we see the p-value. P-value, we also get the same conclusion. Okay. What is p-value? Yeah. So p-value actually is this area, the red color plus the purple color. The red color plus the purple color. Okay. So of course we do know we cannot of course we got formula to compute, but we can skip this part. Because software will give us the p-value. Okay. So therefore we do know the value, but roughly it should be about around 0.04, about 4%. Because this purple color is 2.5%. But okay, can you see? This whole area is 5%. Yeah, 1.645 until the positive infinity is 5%. Okay. So therefore, 1.82, the area must in between 5% and 2.5%. Let's say 4%. Okay. Of course, we should use the whole diagram. Therefore, it's 8%. This p-value is 8%. Okay. But you see, 2.5%, actually we call this alpha. It's 5%. When we consider two tier, it will be 5%. Okay. So therefore, I mean, how we compute this value? We use the table. Yeah, it's critical value. Therefore, we did not call it p-value. We call it critical value. Okay. The critical value, I mean the area bound by this critical value, we did not call it p-value. We call it alpha. So alpha is 5%. Okay. Therefore, p-value larger than alpha. We cannot reject the null hypothesis. this is also it is a more important golden rule for us. P-value larger than alpha, we cannot reject the null hypothesis. Okay. Therefore, we have the same conclusion with the method just now. Remember just now the critical value approach. Now it's a p-value approach. Yeah. But either method, either approach, we have the same conclusion. Yeah, it means at 5%, we cannot reject the null hypothesis. Okay, any question is? Okay, so if no, wait. Okay, so again, so this section not going to mark attendance. Yeah, I only mark attendance two times. Yeah, now and also the next section. Okay, so continue. Yeah. So and then we can also discuss one more minute when the alpha is 5%. Yeah, therefore, okay, just now with alpha 5%, we cannot reject the null hypothesis. Okay, but now we use alpha 10%. You can see, so alpha 10%, and then p-value no change. The p-value now 8% smaller than alpha 10%. Therefore, we reject. We can reject the null hypothesis. Okay. Therefore, still consistent, yeah, with the conclusion just now. Okay. Okay. So if no question, now we see a bit more. So how to compute the p-value? The p-value come from the your own data set. Yeah, but alpha is defined, yeah, by some theorem. Yeah, this is different. Meaning that everybody use 5%, 1%, and also 10%. But p-value will be different for different people, for different capstone. Okay. So this is the alpha and also the p-value. Okay. So of course, for us, including your capstone, actually the p-value is much more important. Okay, you see the reason now. Yeah. Okay. Because if you want to use critical value, you must use the table. Yeah. Okay. The table we got z, we have t, we have chi-square, you have binomial, Poisson, a lot, yeah, many. Yeah. Of course, all correct. But meaning that if you want to use this method, you must know how to read the table. Okay. So of course, z and t are the most important distribution. Yeah. But you may also use other distribution. Okay. Therefore, you need to spend more time here to do the critical value approach. Therefore, we use p-value because the output from the software, normally they give us the p-value normally. Therefore, we just compare p-value with alpha. P-value smaller, reject. P-value larger, cannot reject. Is it? Okay. Of course, reject means always refer to reject the null hypothesis. Okay. This is the p-value. Therefore, make our life easier. Yeah, p-value actually make our life easier. Okay. Okay. And for us, we are going to use the SPSS and also MOS. Of course, yeah, both. Yeah. Okay. So for this one, actually they show us the SIG, yeah, as a p-value, meaning that in the output when they show SIG means it is p-value. Okay. In the SPSS, they show us SIG means p-value. SIG means significant value. Okay, it's p-value. Okay, so if no question, now we see next. Yeah. We are here discuss the power, and then the second power already done. We see the third one, which is the sample size. Okay, sample size. Okay, so sample size increase, the power increase. Okay, we see this now. Okay, so here I can use a different example, which is the yeah, the regression. Okay, of course regression we also discussed a bit just now, not yesterday. Yeah. Okay. Okay. So we see, of course, we discussed already the reason, yeah, why the hypothesis looks like this. Okay, beta is equals to, let's say beta 1. Beta 1 is equals to 0. Beta 1 is not equals to 0. Okay. Okay. So for this one, we can also do the testing here of the hypothesis. Okay. So what we do, we can compute the t. Yeah. T. Okay. T and Z actually quite similar. Yeah. I think no need to go for so detail, but I can say T and Z actually quite similar. The main difference is that okay. The first difference is that the T basically is for the small sample. Yeah, small sample property. Okay. So and then the good point is that both actually having a similar curve like this. Z and T quite similar. Okay. Yeah. So this is the Z and T. Okay. And actually because of this, in the SPSS, they did not show us Z, but they always show us T. Okay, they always show us T in the output. Okay. So we see the T, therefore we can also compute the test statistics here for the T. This is the formula, yeah. Beta over standard error of the beta. Okay. Okay. So we see for the in general, the standard error is like this: square root sigma over square root of n. Yeah, in general. Okay. Of course, this one is a bit different formula, but actually it's something like this. Yeah, sigma over square root of n. Okay. Okay. So therefore, when okay, we see example now. Case A and case B. Case A, same beta. Beta, let's say, is 3. Yeah. Okay. Sigma, let's say, is 5. Yeah. And then square root of 100. Okay, calculator. Okay. So here's 5 over square root of 10. Okay. Therefore, we know A, we have the larger sample size. Yeah, in A compared to B. A 100, B is 10. After that, we can find the value here for the A. Okay. So for the A, 5 over 100, no, 5 over 10. 5 over 10 and then 3 over 0.5, we get 6. B, 5 over square root of 10. And then 3 over the answer, we get 1.897. Okay. So test statistics for A is larger. Therefore, it's easier for A to reject the null hypothesis. For B is smaller. Therefore, it's not easy to reject the null hypothesis. Okay. So of course, we know we still can reject the null hypothesis at 10%, but not 5%. Remember? I mean for two-tail. Okay. Z and T quite similar. Okay. Therefore, the critical value still will be quite similar. Just a bit different not much. Right? Okay, so this point is to discuss the third point. Okay, so means when sample size is larger, the power increase. Yeah, sample size larger, the power also increase. Yeah. So we are here. So means we done already the three factors. Yeah, they can actually affect the power. Okay, you see, the sample size increase, the power also increase. Yeah, if really, okay, this point done. Okay, so now this one will link to your field. Yeah, because you are more to data science, therefore it's also linked to big data. Okay. So if really large sample sizes, even very small effect can be statistically significant. Okay, example. So example. Now we can use Z. Let's say Z. Yeah. Yeah, Z. So here, let's say is remember the formula x bar, okay, minus mu sigma over square root of n. Yeah. So x bar minus mu over sigma over square root of n. But now n is let's say it's 2 million. Yeah, n is let's say 500. Okay. Now we see one example here for 2 million. Therefore, you see we use very small effect. A small effect size. Can you see here? Where is it? Where is it? Okay, here. Yeah, small effect means effect size small. Okay. Effect size small example. Let's say 3.2 minus 3. Yeah. So here still the same. Therefore here 3.2 minus 3. But now here sigma, let's say sigma is 10. Okay, square root of 500. Okay. So 10 over square root of 2 million. Remember? So let's say case A, A and B. Case A really big data, 2 million. B only 500. Okay, much smaller. Okay. So now we can do calculation to find the test statistics. Okay. So 10 over square root of 2 million. Yeah. So and then 0.2 over the answer. Yeah, you get 28 something. 28.28. Okay. Okay. So here is 0.447. Okay, I think check again. Yeah. If my calculation wrong, you let me know. Yeah. 10 over square root 2 million. 0.2 over the answer is correct. Okay. Okay, correct. Okay. So this is calculation. Not finished. Okay, but any question you want to ask is. No. Okay.
So just to recheck,
Yeah.
I recall this T distribution is used for, as you say, is for small sample. So from the book I read is normally you use the number size of 30. If it's less than 30, then we use the T distribution. Is that still valid?
Okay, good question. Thank you. Yeah. So for you, actually we got three factors to determine whether should use T or Z. But sample size is one of the important point. By default, it's correct. 30 and above use Z. 30 and below T. This is one of the factor. Actually, another two more factor. The sample from each population, and then sigma non or unknown. We got three factors. Okay. But actually, for us, only to see so detail. Okay. So it means we just see. You can actually move the same because even the SPSS they will report only T, not no Z. Okay. Yeah. Okay,
It
so
means SPSS, even the sample size is even more than 100 or a few thousand, they also use T.
it's correct, correct. This is SPSS, yeah. Okay.
Ah,
So,
okay.
yeah. Okay. Okay. So because this again, this no different not much, yeah. Different not much when it come to the large sample. And SPSS, maybe they assume that we always use large sample, means 30 and above. Let's say you are master, even degree in APU, minimum they must have 100. I mean, the sample size must be 100 and above for degree final year project. Then 500, 100 and above. 100 above confirm already use Z, not T. Okay.
Okay.
Okay. Thank you. So we see. Now we are still here. So now we see. Therefore, this is the conclusion. When the sample size is large, it's really easy for us to reject the null hypothesis. And remember, this is test statistics. Test statistics larger means easier for us to reject the null hypothesis. 500, we cannot reject, but 2 million, we can reject the null hypothesis. Okay. Okay. So if no problem, now we see what you should do. Yeah. I mean, therefore, this will be a little bit not practical for you, yeah, because you always get large sample size, right? Not, yeah, either from bank or from Macy's, or from DG, yeah. Big data, of course, easily your sample size is more than million. Right. So therefore, okay, we see the idea, yeah, you can see. Therefore, the issue is the practical significant and the statistical significant, meaning that for this case, 28.28 is statistical significant. Yeah, we can reject the null hypothesis. Therefore, it's significant. The result is significant. Okay. But is this practical significant or not? Okay. So I give you some one method on how to handle this to make sure that your result is practical. Okay. 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 So what you do, you can do like this. Yeah. 2 million, yeah, 2 million sample size. You can make it a small, you can separate it to many small sample. Let's say 5 million, 5,000. N1 5,000, N2 5,000. And then they are all can be mutually exclusive. Let's say the respondent already in the group 1. The respondent already in group 1, let's say the user, the Maybank customer, already in this group, therefore not in this group anymore. Yeah, it's independent. Okay. Mutually exclusive. Okay. So you use this 5,000, N1 you do testing. Therefore you will get X bar minus mu, yeah, sigma square root of N1. X bar minus mu over sigma over square root of N2. Therefore, you got many testing. You see the result later. If here, any question on this method? Okay. So if not, now we see. After this, you see you compute the test statistics. Yeah. Let's say all are high. Here 4.2. Here is 5.2. Here you get let's say 6 something, and so on and so forth. Meaning that your result is still considered good, is significant. Means the result is significant even you use a small sample. Let's say 5,000 like that. Okay. So this is one of the method that you can use. Okay. Okay. Because the result actually easily affected by the sample size. Okay. So already mentioned here, you see, the power is easily determined. You're easily affected by these 3 factors, especially sample size. Okay. So people may question you, yeah. People may question you, why you use 10%. 10% easy to reject the null hypothesis. If people ask you 5%, okay, use 5%. You cannot, you cannot, you cannot determine the effect size. It's from data. You cannot change the data. Okay, but for you, yeah, depends on your project. Right now, let's say your data from Maybank, yeah, from DG, confirm got many users. Okay, so therefore the result will be good always. Okay, therefore the result will be practical significant or statistical significant. Okay, it's another issue. Therefore, you can use this method to handle it. Okay, yeah. So that people your conclusion will be more convincing. Okay.
I said just to recap, your small effect means even though the bar X is very close to the mean,
Yes, correct.
the 3.2 to 2, so that's why. But when the sample size is big, then it's still very significant.
Yes, correct. You are right. Correct.
Okay. Thank you.
So the effect size meaning that is the difference between the X bar and also the mu is small. Yeah. So 3 and 3.2 is small. Okay, correct here. 3.2 and 3 here is small size. Yeah. So here also small size. Yeah. But when the sample size is small, 500, therefore cannot reject the null hypothesis. Okay. But when the n is 2 million, therefore can easily reject the null hypothesis. Okay. Therefore,
also, if let's say the Z value is same as our critical value, what is the result? Should we reject?
Same.
I mean, if the Z value is the same as our critical value, what should we do?
Okay, good question. But it seldom happen. Okay, it seldom happen. Why not? In your life, this question is a statistical, it's a theoretical question, but it's not a practical question because it seldom happen. Okay, it's example. Example. Okay. Uh, it's more to, it's very academic. Example, let's say your weight is okay 65.28. You think easy or not for you to find another person with the same weight with you? It's difficult, right? It's very difficult. Yeah, therefore it's not a very practical question. Yeah, okay. But in case this happen, then how? Okay. You may refer to some textbook. I can answer this question. Okay. Yeah. Okay. But for the p-value, yeah. But for the p-value in general, p-value smaller, yeah, then alpha will reject the null hypothesis. Okay, so it must be small. But again, this small also meaningless because you get 0.0 p-value, yeah, 0.05. Here also 0.05. You see? Okay. Therefore, people may say this result is not good because it's too sensitive. Why is not why sensitive? Because say this one happen, your n is only 1,000, but you get one more person. This person will affect the result. Correct? Yeah. You see, this only one person but can affect the result. Become from significant to not significant. If for this result will be actually too sensitive. That means not too good. You may increase not only one person. I mean, you can increase sample size, but maybe not one, maybe more. Yeah, 10 or 20 like that. Okay. Okay.
So, thank you, sir.
Yeah. Okay. Thank you. See you next. Okay. So we done already this part. Now we see next. Yeah. Okay. Again, I have to remind you on the software. Yeah. So next chapter, maybe tomorrow we are going to use the software, or maybe today. Okay. Therefore, make sure you install the SPSS. AMOS not too urgent. Yeah. SPSS is more urgent. Okay. See now. Yeah. So this is the diagram. Yes, correct. Here. Okay. So we see these are three factors. It can affect the what they call the power. Yeah. The sample size. Okay. You see, this is the sample size, the horizontal. Yeah, the sample size. Okay. So the vertical is the power. Therefore, yeah, as we mentioned just now, when the sample size increase, the power also increase, but not linear. Okay, it's increase but not linear. The linear means straight line, but now it's not. Okay. It's the first. Okay. Then we see 0.1 alpha 10%, 5%, and also 1%. Okay. So we see, let's say we see, yeah, I think we can wait. Okay. We can see these 3 points. Okay, we maintain the power at 0.8. Therefore, we see 10%, 5%, and also 1%. Meaning that 1%, you need larger sample size to achieve the power of 0.8. Can I see? You need larger sample size, maybe about 190, about that. But 5%, you need only about 132. Yeah, it's smaller. Smaller sample size, you can achieve the power of 0.8. Okay. So therefore, larger alpha, easy for us to reject the null hypothesis. Remember, power larger means easier for us to reject the null hypothesis. Okay. This is the sample size and the alpha. Okay.
So the power is only dependent on these two variables, which are the sample size and the alpha, right?
And also effect size.
Or effect size.
Yeah.
So three.
Here we did not handle the effect size in this diagram. Yeah. But we already discussed, right? Effect size larger means easier, means effect size larger, the power increase. Power increase easier for us to reject the null hypothesis.
So the effect size here is the difference between the bar x and the mean, right?
Yes, correct.
Okay.
Correct. It's between the x bar and also the mu. Correct.
So it seems to be with this kind of curving, there's a formula, right? To put in all these formulas in variables into a formula.
Okay. Good question. So no, actually this one is just the calculation. Is it this calculation? Yeah. So you see, power is 1 minus beta. Yeah. So of course, this is a formula to do the calculation. Yeah. So okay. I think no need to be so technical. Okay. You just understand the concept, the idea.
Okay.
Thank you. You can see. Next. Yeah. Okay. So this one actually is more to a revision for what we discussed just now. Can you see? So researcher should always design the study to achieve a power level of 0.8 at the desired significant level. So 0.8 is already considered good enough. So let's say 1% more stringent, meaning that 1% means 1%. Yeah, because 1% means it's not easy, more difficult for us to reject the null hypothesis. Therefore, it required larger samples to achieve the desired power level. You need 190 for you to get the power of 0.8. So therefore, you can also take 10%. 10% therefore not that strict. Therefore, it's easier. Easier for us to increase the power, and then also easier to reject the null hypothesis. So smaller sample, let's say 3.2 minus 3. The difference is only 0.2. Therefore, it's smaller effect size. Therefore, you need larger sample size. Like what we used just now, 2 million. Okay, maybe more. Yeah. So for us to achieve the power. Okay. So you need that. If you see the smaller your effect size is small, you can increase the sample size for you to reject the null hypothesis. Yeah. But again, people may still question you. Yeah. Okay. People may question you also. Why you take so many? Why your sample size so large, so big? Okay. So therefore, yeah. So any increase in power is mostly achieved by increase the sample size. So therefore, you still need to justify why you use the large sample size. Okay, any question for this part?
So just a general question. It means
Yeah.
we can always like, I'm not sure, is it the right way to say we can like choose which significance we want to achieve our desired power, right? I mean, if we find some result that is cannot reject, but then you choose a lower, or no, sorry, the higher alpha, then you can accept it. So it's how we choose the significance level.
Understand. Okay, so this one actually, you are right. Meaning that if you, I know your question, yeah. You saying that it looks like you can manipulate the result, yeah, but means you say that.
Yes, I don't want to use the word manipulate.
Okay. No, something you are implicitly that's your idea, right now. Okay. Yeah, alpha 5%, therefore you cannot, you cannot reject the null hypothesis. Yeah, therefore you use alpha 10%. Yeah, therefore you can reject the null hypothesis. So some may think that way, but actually not too easy, because it's quite standard that your supervisor will tell you we want 5%, not 10%. Okay, so and then even you submit your paper to journal, then they will also question you why you 10%, why not 5%. Okay, so means 10% means not too convincing. And remember, 5% alpha is the Taiwan error. Yeah, alpha is Taiwan error. 10% means the result not too convincing. Okay, not too convincing. You compare to 5%. Okay, so you see, for 1%, yeah, some study they want 1%, yeah, especially linked to some medical, yeah, medical related study they want 1%, because it involves people's life. Okay, so let's say for some business finance management, 5% still okay. So depends, yeah. So means you cannot easily change the percentage, make it significant, not like that.
Yeah, and then there is no like 4% or 3%. It's like a 1, 5, 10.
No, it's 1, 5, 10. This is a standard. Okay.
It's like a market acceptable range.
Yes, correct. Okay, so people normally want 5%. Yeah, normally, yeah.
Okay. Thank you.
Okay, so if no question, now we see next. Wait. Oh, okay. Sorry, where? Why did it appear just now? Okay. Okay, see first. Yeah. Where? Okay. One by one.
I just want to check with you the Z value and the P value, the concept of the operator, is less than or equal, is opposite, is it? The Z value and P value, we have to do the test.
See first, one by one. It's okay, don't worry. I see first. Okay. So Z value more than critical value. Z value here refer to the test statistics. Larger than the critical value, it should reject the null hypothesis, correct? Yeah. Okay. But P value, we never compare if critical value.
Significant level.
You should compare if the alpha. Okay. So if you want to use the, can you see P value, you must compare with alpha. Okay now, yeah. Okay. It's like that. Okay. So P value compare with alpha. P value smaller than alpha, we reject the null hypothesis. Yeah. So be careful. Okay.
So one more question. If I want to increase the power, either I can increase the sample size or the effect size, right? But effect size is quite difficult to change, right? Because it's something related to the sample mean we cannot simply change already. So the only thing we can we can change is the sample size.
Yes,
to increase the power. Thank you, sir.
You are right. Okay, now we see next. I know the answer. Is it okay? P value smaller than alpha we reject is correct. This is correct. Okay. Okay, this score is how far the value is from the mean. This score, this value. I assume here you're mentioning about the test statistics. Okay. So test statistics. Okay. Not like that. Test statistics. It's not only how far, also consider the standard deviation and also the sample size. Okay. You see the formula? Yeah. Can you see? For three factors. Three factors will affect the Z score. Here is the test statistics. Okay. So the gap here is the effect size. Okay. So first thing, therefore the Z value depends on the effect size, sigma, and also the n. Okay. Okay. I can tell you the relationship. Effect size larger, Z also larger. First, okay. So second, when sigma smaller, Z will be larger. Okay, so sigma is a standard deviation. When the sigma is smaller, therefore Z will be larger. Therefore, easier for us to reject the null hypothesis. Okay. Therefore, if your data is, therefore, of course, you know this is standard deviation. Okay. So if the data, the variation is too high, it's not easy for you to reject the null hypothesis. Okay. So n larger, Z will be larger. Z larger, the power also larger. Okay, therefore easier for us to reject the null hypothesis. Okay. Okay.
So Z score is basically the term you use, like we normalize the data, is like changing to a Z score. Is it
correct? You can say so. We normalize it. We normalize it. So because x can be any variable, but we normalize it. You're right. Correct.
okay?
Yeah. We normalize it. Yeah.
So in this subset, do we cover any non-parametric? Currently, we are cover on this parametric distribution, right? Normal distribution curve.
Correct.
Thank you,
This is
sir.
considered parametric. Yeah, correct. Parametric. Yeah. Okay. So, okay, now we see one more p-value. P-value is probability of the event happening. No. Okay. Okay. A little bit technical p-value. Yeah. So p-value. P-value is the exact. We call it is exact probability. Yeah. Okay. Okay. Which is the actually it's exact probability, and it come from the data. Yeah. Okay. Okay. Actually discussed already. Is it just now? Remember? Okay. Okay. So this is the okay 1.96 is the critical value. Yeah. But let's say your test statistics is 2.18. This is your test statistics. Okay. Which is the Z score. Okay. So therefore this small area is the p-value. Yeah, p-value calculated based on your data. Okay. Okay, if no, wait. I think maybe don't get finished to answer the question. Yeah. Okay, wait. Here. It's correct. Okay. No, this is previous. Okay, go. Okay, go. Okay. So, okay. Okay, it's okay. Don't worry. I can start from the beginning. Yeah, on how to use the SPSS. Okay. So later we see how. Yeah. So we see first. We continue with the discussion. If no question. So now we are here. Yeah. Okay. This one done. This one done. Okay. Now we are here. Okay. So we got dependent technique and also interdependent technique. Okay. We see this one. Okay. So we see first the first category. Okay. We got two. First is a dependent technique. Meaning that the model, it must define very clear. It must define very clear what is your dependent variable. Okay, and then this dependent variable depends on other variables. Okay, so it's a variable or set of variables. It's defined as the dependent, yeah, and then to be predicted or explained by other independent variables. Okay, like that. So this module, you focus more on this few, multiple regression, and then discriminant, logistic, and then SEM. The rest are not much. Okay. So you see this four, yeah, under the dependent techniques. Okay. Okay. Next is interdependent. Okay. So interdependent meaning that actually it's like this. In your data set, let's say you got 10 variables. You cannot say which one is the dependent. They're all same level. You can say all same level. This is the interdependence technique. Okay. So we simultaneously analyze all the variables here in the set without distinction between the dependent or independent. Means all the variables same level. Okay. So you'll see two. Yeah, this one and also this, the first and second. Actually, it's only the factor analysis. Yeah. Okay, and also the CA, FA and also CA. CA means cluster analysis. You'll see these two. Okay. Okay. If no question, now we see next. Yeah. Okay. So now, is some question. Yeah, some technique. Yeah, some technique. Yeah. So example, the first one, which technique you should use? You can say which technique you should use. Yeah. So there are many. Yeah, there are many techniques. Okay. So first question. Yeah. What types of relationship is being examined? Okay. So example. Yeah. Okay. Example. Yeah. So. Okay. Some of you may learn this, may use this in your final year project, in your degree. Okay. Example, you want to do this, the impact. The impact of, let's say the impact of independent variable on the dependent variable. Okay. Okay. Example, the effect of, let's say, royalty. Yeah. Royalty on purchase, your purchase intention. Okay, some popular topic under the business. Okay, I see. Therefore, this is the dependent. Okay, this is the dependence because it's clearly defined the effect of this is independent. This is dependent. You clearly define the independent and dependent. So you have to find the effect of something on other thing. Remember the cause effect. Okay, so this one means you should use the dependence technique. Okay. Okay. So if no question, okay. Okay. If no question, we see next. Yeah. Okay. So for the interdependent, okay, we see example also for the interdependent. Okay. So the factor analysis, basically for the factor analysis, we want to group them into few factors. Let's say you have 20 items. You want to, because too many, you can group them into maybe let's say four or five categories. Example, why some employees always late to office. Example, okay. So maybe because of transport, they say therefore they may give some reason. Yeah, example the car breakdown. Example the traffic jam. Okay. So example no petrol. Example. Okay. So this one maybe they say send the children to the kindergarten. Example. Okay. And then any other example? Yes. Okay. Send the kids to the to clinic. Example. Okay, and so on and so forth. Okay. So this all therefore this is more to family related. This transport means there are many items you can group it into a few categories. There are a few factors. Okay, we call it factor analysis. Okay, so okay, but this one you cannot say which one affect which one. They are same level. Okay, we call it interdependence. Okay. And then next, yeah. For the dependence technique, how many variables are being predicted? It means how many dependents, how many dependent variables you have. Can be one, can be two. Okay. Let's say for this one, of course you should know this already now. Yeah. For the multiple linear regression, you must have only one dependent. Let's say you got two dependent variables, then you may consider structural equation modeling. Okay, I see. Therefore, you must know your research objective, what you want to do, what you want to do with the data. Okay. Okay. So if no question, now we see next. What is the measurement scale of the dependent variable? You see, we discussed this already yesterday about the measurement scale. Now we see how it will affect the selection of the model, okay, of the technique. Okay. So let's say your dependent is metric. Okay, it's metric. Example, let's say income. The family income affected by many factors, including education, labor, including the experience, and so on and so forth. Okay. Therefore, it's metric. Income is metric. Okay. So another one, non-metric. Non-metric. Yeah. Non-metric. Let's say you apply for a job. Either the company will offer you the job or not. Therefore, only okay, you make it three. You make it three categories. Yeah. So first accepted, second KIV, yes, third rejected. Okay. I mean normally they didn't tell you rejected, right now? Yeah. Either accepted or KIV. Okay, normally. Okay. They say two categories. Therefore, this two is not number, it's a non-metric. Okay. Therefore, this one can be affected, can use the other thing. Yeah, it's non-metric. Metric, we can use multiple linear regression. But non-metric, we can use logistic. Okay, logistic regression. Okay. Yeah, correct here. Can see the third one. Okay. Okay. So therefore, the measurement scale will affect the selection of the technique. Okay. So of course we will see also these two. Yeah, the multiple regression and also the logistic. Yeah. Okay. So okay. If no question, now we see next. Yeah. So now we are okay. We are here. Okay. Okay. What is the measurement scale of the predictor variable? Means is the independent. Okay. So if your independent variable can be non-metric. It can also be metric. Okay. So this one also will affect the what they call the selection of the technique. Okay. So example, yeah. Yeah, we are going to see this also later. Obviously, a little bit now. Let's say you want to use multiple linear regression. Okay, be careful. You suppose use this for your what? For your assignment. Yeah, your assignment you should look for data. Okay, the data that you should look for actually all should be metric. Okay, yeah. Okay, I'll show you now. Assignment. Okay, assignment. So you should look for your own data. Can see at least 100 cases. Yeah. Okay. At least 100 and then all metric. Can I see one metric dependent and then at least 8 metric independent variables. Okay. So you find data and then send to me. If you are sure, okay. If not sure, you can send to me. Yeah. Okay. So okay. So minimum 8 metric independent and minimum 1 metric dependent. Okay. So let's say your data that is means you can use the multiple linear regression. Okay. Okay. So if no problem, now we see what happened. Yeah. If your dependent is a non-metric, therefore you can use the dummy, dummy variable. Okay. So example. Okay. So okay. So example, let's say you believe that the student in the urban, they can perform better compared to the student in the rural area. Yeah. So therefore, this is the non-metric. Yeah. Okay. This is non-metric, and then this one can affect the academic performance. Yeah. Okay. Therefore, like this. Okay. So for the dependent is the academic performance. It's easily can be metric. Yeah, because let's say you use their marks in the max exam result, it can be therefore it's metric. Okay, but how to handle the urban and rural? Yeah, so we can use 1 for urban and then 0 for rural, like that. Okay, you will see more detail later. Means what we do, we can adjust a little bit on the equation. We still can handle if the independent is a non-metric. Okay, still can handle. Okay. Okay, so yeah, so because as I mentioned also yesterday, so sometimes we can determine what data you want. Let's say you want your data to be metric or non-metric. Sometimes you can determine, sometimes cannot. Let's say data from the Silcom, okay, therefore you just use it. You cannot change anymore. Okay, just use it. Yeah. If you prepare the question by your own, you may consider to adjust or modify or construct some question for you to get the metric data. It depends. Okay. Therefore, you must know both. Yeah. Means both means you must know how to handle metric and also non-metric both. Okay. Okay. So if no question, we see next. Okay. So for the interdependence technique, are you examining the relationship between the variables, respondents or objects? Yeah, means you're focusing on the respondent, let's say the people, or their opinion, and so on and so forth. Let's say the commitment of the respondent. You're focusing on the commitment or different group of category. Can I see? Yeah, commitment is the variable, but respondent is the people. Which one your focus? Okay, you will see this also. Yeah. Okay. Okay. So next we see. Yeah. Okay. So we got two broad types of multivariate method. Dependence. We analyze the dependence and the independent variables. Yeah, at the same time. Yeah, cause and effect. Okay, so it must define very clear what is your dependent, what is your independent. But this one, no need. You no need to distinguish. Yeah, these two. Yeah, no need. Okay, so they are same level. Okay. So therefore, you got two main methods. Okay, dependence and also interdependence. If only one dependent can be also few dependence variable. Okay. Okay. So you see the left side, the leftmost. Yeah. The dependent can be metric. Dependent metric, therefore you can use the multiple linear regression. Okay. Conjoint not going to focus. Yeah. Your dependent can be non-metric, discussed a bit just now. Either your application will be accepted or KIV. Yeah, therefore it's different non-metric, different category. Okay. So therefore, this one can be discriminant analysis or logic. You will see this both. Okay, in this module. Yeah. So discriminant meaning that is a multiple discriminant analysis. Okay. So can be also several, yeah, several dependent variable, but we're not going to see that much on this. Okay. Okay. So this one is a bit more advanced. It's multiple relationships structural equation, meaning that we use Amos later. Amos, yeah. Okay, means you got few dependent and few independent. Okay, therefore a bit more advanced. You will see also, yeah. Okay. So and then also you will see interdependence method. Yeah. So you see the all metric. All metric, you see two only, FA and also CA. KLC all must be metric. Therefore, your assignment use this and also the multiple linear regression. The data must be all metric. Okay, you can start to look for data first. Okay, this is the overall picture on the multivariate methods. Okay, any questions? Yes. Okay. Okay, so if no problem, now we see next. Oh yeah. Make sure no problem. Wait. Okay, good question. Okay, good question. Okay, good question. Actually, no need because okay, your friend asking the mediating or modulating. Actually, no need because this one is for the SEM. Yeah. So you advanced. Yeah. Okay. Okay. So this one will be under the SEM. Yeah. SEM we have a mediating variable and modulating variable, but your assignment only cover two topics. Multiple linear regression and also the factor analysis. Okay. Okay, you can see a bit now. Yeah, you can see. Question 1 about the multiple linear regression. Question 2 about the factor analysis. Sorry. Yeah, okay. Can I see question 2 about the factor analysis? Where is it? Yeah, correct. Can I see here? Factor analysis. Okay. But what you mentioned just now, mediating, modulating is under the structural equation modeling. Okay, this is the last chapter of this module. Right. Okay, so okay, done. Okay, so we see next. Yeah. Okay. So now we see a quick review on each method. Yeah, and then we start chapter 1. I think today. Yeah, today you can see chapter 2. This is chapter 1. Okay. So we see multiple regression. Multiple here means minimum two independent variables. Most of you should know this. Yeah, if you still remember what you learned in statistics. Okay, yeah. So this is example of the multiple regression. Okay. Okay. Therefore, it's single metric dependent variable. Only one metric dependent variable. The dependent variable must be metric. Predicted by several metric independent variables. All must be metric. Yeah, in your it's what you should do in your assignment. Okay. Okay. So, for example here, y affected by x1 and x2. Yeah, same if the equation I show you in the slide. Okay. Okay. Now this one a little bit new for some of you. I think for most of you, okay, it's a little bit new. Okay. So means normally you didn't learn this in other module. Yeah, okay. We see this one actually linked to your the machine learning. Yeah. Okay. You may learn this in machine learning. No, you learn machine learning. This is one of the method under the machine learning. Yeah, we call it supervised. Okay. We call it supervised machine learning. Okay. So we see now. Yeah. Right. So we have one if a single non-metric dependent variable. Yeah. The dependent variable is non-metric. Yeah. But can be 2 or 3 categories. Okay. Okay. So example here, you see gender got 2, and then culture can be USA and outside USA. Yeah. For the online shopping, can be you want to identify who are the purchaser, who are not. Yeah. Okay. So member or non-member, the good, average, and poor credit risk. So for the bank, either the bank should approve the loan or not. Is it housing loan or credit card loan? Okay, sorry, credit card. No loan, it's credit card. Okay. So the bank should actually approve or not. It depends on their some factors. So the factors, we call it metric independent variables. Let's say for this one, for credit card, the credit risk can be the income, can be the commitment. Yeah, can be the what they call the credit score. Yeah, okay. From the I think Malaysian should know Malaysian should know kekris, something like that. Something like that. Okay, it's under the central bank. Okay, means you borrow money from bank A, yeah, but you did not settle it. Then you apply credit card with bank B, you cannot get the card anymore. Yeah, because the bank A will report your case to the Central Bank of Malaysia. Okay, this is the system. Okay. Okay. So yeah, some of you may be from the banking, you know better than me. Okay. So you see, this is the discriminant analysis. Okay. Okay. Any question for this? So we call it supervised machine learning because in this case you can use this method when the group is non. Yeah, when the group is non, means you have the data already. Yeah, example you have the data already for the this one good average in the poor credit risk. Means you got one column you call credit risk, good, average, poor, like that. Okay. So let's say you do know, then you should use the cluster analysis. Again, if you know the group already, yeah, let's say the person is more to follow the US culture or outside USA culture. You know already. Therefore, you should use this method, discriminant analysis. If you do know, therefore you can use the cluster analysis. Okay. Okay. So cluster analysis is unsupervised. It's also machine learning. It's unsupervised. I mean, one type of analysis under the machine learning. Okay. So CA is unsupervised machine learning. Okay. Okay, any question? Yes. No, okay. So you will see more detail later, including how to use the software, yeah, to do data analysis. Okay. Okay. So if no question, now you see logistic. Okay. So logistic is a single non-metric dependent variable. Okay. But here is a bit specific because the dependent variable must be only two categories. Must be only two categories. Yeah. Okay. Example. On the house or not. Can you see? On the house or not. Okay. So means even apartment flat consider house. Okay. You make it you must define it very clear. Okay. Even you don't get settle the loan, but still own the house. Once you sign the agreement. So once you get the key, maybe, and yeah, okay. So therefore, you start to pay the installment, not get finished, but you still own the house. Okay. So therefore, this is the only two categories. Okay. So and then can be predicted by several metric independent. Okay. Example, maybe income, maybe the family size. Yeah. So okay. Therefore, the larger in general, they say a person with a larger family size, they tend to buy a house. Okay, in general. Okay. So therefore, these two factors can be important independent variables. They can affect the ownership of a house. Okay. Okay. Therefore, this is quite similar with the discriminant analysis. Yeah, but using this method, we will get a equation. You will get equation. Okay. So basically, it's like this. Pi 1 minus Pi log. Yeah. Okay. So therefore, we adjust a little bit beta 2 yeah, for the logistic. Okay. So you will see this later. Okay. Okay. I mean, there's a difference between this method and also the discriminant. That we discussed a bit just now. You will see more detail later. I mean, for the discriminant and also the logistic analysis. Okay. Okay. If no question, we see this one. Just go through a bit because I'm not going to discuss too advanced. This is ANOVA. Yeah. MANOVA is multiple analysis of variance. Yeah. So it's quite similar with the ANOVA. Yeah, ANOVA, you should learn this also in the instead just a little bit. Okay. Okay. But here a bit different because we got still several metric dependent predicted by non-metric categorical. Okay. So but it's okay, not going to see too much. Yeah. But just that in case you have this situation, you may also look back, let me study more detail on how to use MANOVA. But not our focus in this module. Okay. It's also several metric dependent predicted by several metric independent. We can do this also using the SEM. Okay, you see SEM not this okay, not this method. Okay, so also not going to discuss too much in this module. Yeah, we see SEM. Okay. So this one is a little bit more complex because we estimate multiple, interrelated dependence relationship, okay, based on these two components, measurement and also the structure. Okay. So example, we see a bit more. Then we see more detail later in the final chapter. So example like this. Yeah, we see a simple one. Yeah, A affect C, B also affect C. If like this, it's only multiple linear regression. So you see, under the structural, under SEM, structural equation modeling, it can be more complicated. Okay. Example like this. You see, A may affect B, but A also affects C. Okay. So example, age. This one can be the maybe not too good. Age not too good. Example. Okay. Okay. Let's say commitment. Let's say motivation. Okay. Let's say here is the performance. Okay, the work performance. Okay. Okay, like this. Therefore, commitment affect more commitment affect higher motivation. Okay, or maybe the other way around. Maybe like this. Can I say? Commitment affect motivation. Motivation affect commitment. Commitment affect the work performance. Motivation also affect the work performance. If like this, then become the simple model under the structural equation modeling. Okay. Okay, any question so far? This is this diagram can be used to discuss the this one, the structural model. Okay, we see the measurement model now. Okay, so we can use different color. Yeah, we add a bit more thing, then it will be the measurement model. Okay, so this one also discussed a little bit in the previous class that we may have, let's say, 5 items. Yeah, for us to measure the commitment. Can you see? 1, 2, 3, 4, 5. We include this also in the model. Okay. So here can be also another 5 items. Yeah, for us to measure the motivation of the employee. Can you see? Therefore, these 5 items is to be used to measure the commitment. These 5 actually are to be used to measure the motivation of the employee. Therefore, it's considered the measurement model. If you see only this part is the measurement model, how you use the 5 items to measure the commitment of the employee. You see, everything actually is the SEM, the structural equation modeling. Okay. So of course, we see more detail later in the final chapter. So this one we should use the AMOS. Yeah. Okay. And then here also link to the factor analysis. That's why we see we will do factor analysis. They only do the structural equation modeling. Okay. Okay. This is my advice Okay. This is my advice. If possible, you submit the assignment as soon as possible. Okay. I tell you why. Of course, you should know why. Yeah. Okay. You should know the reason. Yeah. Where is it? Okay. I know already. Don't worry. I know already. Yeah. Okay. So if possible, you do your assignment as soon as possible because okay, can you see? Once you finish the first 2 chapters, you already can submit the assignment. Assignment only need first two chapters. Okay. Okay. So because if you submitted late, then later the quiz 1, quiz 2 test will come. Okay. We cannot do the quiz 1, quiz 2 and as test too soon because we cover the more chapters. But assignment you can submit first. Even due date is 17th October. Okay. So I mean I still follow the due date, but you can submit as soon as possible. Okay. So now we continue with our discussion. Not here. Yeah, I know why. Okay. So we are here. Okay. So this is the second chapter means we finished the chapter 1. No, this is third. Okay. So second will be multiple linear regression. The third will be the factor analysis. Okay. So the second chapter confirm we must use the software already. Okay. So the first chapter not yet. Okay. Okay. So this one we analyze the structure of the interrelationships among the large number of variables to determine a set of common underlying dimensions. Remember just now, there are some you have some reasons why the employee are late to the company. Yeah. So and then you can you can do the grouping. Yeah. So from 20 kind of reason, you make it become maybe 3 or 4 factors. First one can be the transport. Okay. Either the bus delay or the car breakdown or traffic jam is transport. Okay. So another one, send the kid to the clinic, yeah, and so on and so forth is under the family. Okay, family issue, yeah, and so on and so forth. Okay. So this is what we can do under the factor analysis. Okay. Okay. No question, okay. So this is also important for means we will do this also in the assignment, yeah, in assignment, correct. Okay. Okay, good question. So you see, okay. Wayne, you want the assignment? Okay, good question. Okay, next week I'll give you the assignment. Yeah, Monday. Yeah. So Monday I will I'll do the assignment to the Moodle. Okay, Monday. Okay. So assignment, yeah. Deadline. Actually no deadline, but as soon as possible. Yeah. So I I mean you didn't give me. You should not give me last minute. Let's say tomorrow submit assignment. Now you want me to review. It's not proper. Okay. So okay, 1 week before. Okay, 1 week. So before I can give you a new deadline. Meaning that 10 October. 1 week. Okay. So give me some time to review. Yeah. Okay. Oh yeah. I think correct. Correct. 17 17. Okay. Yeah, 17 is correct, before law. Yeah. Okay, so 17 means 10, 1 week before the due date. You can still send me your data and check for you. Okay. Okay. Yeah, since you're asking assignment, I can also tell you one thing also. You when you submit the data file for me for checking, you let me know also the independent variable, your dependent variables. Okay. Okay. Sometimes the sometimes the data file they show me let's say x1 x2, but I don't know what is this, therefore I cannot comment. Can I say means it must mention example x1 is the x1 can be the income, x2 can be the purchase, like that. Okay, means you must let me know the meaning, the meaning of each variable. Okay, let's say the variable mention age. Okay, I know already. Okay, so you must mention. Otherwise, you must mention. Let me know. Therefore, will be easier for me to comment. Yeah. Okay. Okay. It's correct. Xin Zhong Seng, you are right. Therefore, only these two chapters here for the assignment because it's assignment. You can say this is your assignment. Okay. So only 2 chapters. Yeah. Right? This is the first assessment. Yeah. Okay. Okay. So if no question, we continue. So we are here. Okay. Okay, so means the sequence will be quiz 1, okay, we do quiz 1 and then quiz 2 and then test. Test will be final, the final assessment. Yeah, but anyhow, I'm still a little bit flexible. Okay, you may decide later. Okay, you may decide later either you want to use the date given by the admin to do the test. Okay. So remember, the admin give you a date for the exam, but we don't have exam. So previous intake was student requested to use the date to do the test. Okay. So we may do we may make decision later, maybe few weeks before that. Okay. But that's either we do it on that day or do it during class. Up to you. Yeah, I'm okay. 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 So we continue. Yeah. But cannot be later than that. Either use the date for exam for us to do the test, yeah, or we do it during the class. Okay. Yeah. Okay. Well, mock test. Well, good question. Mock test. You want to do mock test? Okay, I can record it. No problem. I can do it. Okay. Okay, I can do it. Okay. Wait, yeah. Okay. So if no mock test meaning that we should actually try to finish the topics, yeah, as soon as possible. Then got time to do the mock test. Yeah. Okay. So anyhow we can try. Yeah. Okay. Okay, I record it first. Okay. Yeah. Okay. So yeah. So continue. Yeah. Okay. We are here. Yeah. So this EFA. So factor analysis. Yeah. Okay. Okay. So this one also we focus more detail. And then as I mentioned just now, this is one of the examples. Yeah. Under the unsupervised. I know it's quite yeah, you will learn a lot. Yeah. So, I mean, you learn a lot in the machine learning. Yeah. This is one of the example under the unsupervised machine learning. Okay. So because the group is unknown. Yeah. Okay. Let's say you just now already use the example for the job. Okay. In the other case, let's say you got data set 10,000 people they applying for, let's say they're applying for a public university. Okay. So and then you have their result, everything. You see? Yeah. But you don't know yet either they will get offer letter or not. Yeah, from the public university. For them to study, to study the degree. Okay. Therefore, you don't know yet the outcome. Therefore, it's unsupervised. Okay. So the group is unknown. Okay. So okay. Okay. So, but of course, you can find 2 or 3 groups. Let's say 2 groups. Yeah. You can do the grouping. Yeah, 2 groups. Yeah. Let's say okay, 3 group maybe is more better. Okay, 1, 2, 3. Okay, 1, 2, 3. Okay. So first one, second, and third. Yeah. Therefore, you may assume that the group number 1 will be will receive the offer letter, yeah, from the public university. Okay. So second maybe likely. Okay, likely. So here likely yes. Likely no. Okay. Okay. Then you can see their result. Let's say you focus, of course, they may apply to the public U using different result. Some may using SDPM, some may using A level, and so on and so forth. Let's say you only focus on the one who use the SDPM and only Malaysian example. Okay, example. Okay, because we know now non-Malaysian also can apply to study in public university in Malaysia. Some okay, okay. So you may find some students with the similar similar result. If the result is quite similar, example, let's say HDPN, okay, some may know, some may not know. HDPN now they also follow the semester system. Therefore, they also have their CGPA. Okay, they say the one with a high CGPA, they group together. They're similar. Okay, this one quite low. It's a middle. Therefore, got 3 groups. Okay, actually they also use their core curriculum. Also can affect the chance to enter the public university in Malaysia. Okay, therefore you can use 2 factors. They call the CGPA and also the score here in your core curriculum. Yeah. Okay. So therefore, you don't know yet the outcome, but you can do the cluster, make it become 3 clusters. The first cluster all are high CGPA, also high core curriculum. So active in the core curriculum. Okay, like that. Okay. Therefore, within the cluster will be quite similar. Yeah, but between cluster different a lot. Like that. Okay. So each object is similar to the other object in the cluster, but different between the cluster. Okay, it's the cluster analysis. Okay, of course we will see also how to use the SPSS to do the data analysis. Okay, later. Okay, this cluster analysis. Okay. Okay. If no question, now we see. Next, yeah. Okay. Okay, so you can see a bit more on this one. Okay, yeah. Okay. So here maybe a little bit technical, a little bit, yeah. Okay. So I mean the first 4 questions still okay, yeah. So the cluster analysis of eating out question. So first one, they eat at the fast food restaurant at least once a week. Okay. So number 2, eat prefer restaurants with the highest quality food. Okay, and then the restaurant that have the quick service and then nice atmosphere. Okay, therefore in general, okay, in general we know those who answer agree. I think 7. Yes, correct. 7 is agree. Yeah, strongly agree. 1 is a strongly disagree. Okay, so the respondent will answer from 1 until 7. Yeah, for these 4 questions. So in general, we know if the respondent answer more to 6 and 7, means is number 1, know how to enjoy because they want highest quality food. Second thing, maybe higher income also. Okay, compared to those who answer 1 and 2 in general. Okay, in general. Okay, so therefore, at least you got two groups. Okay, so I mean 2 clusters. Here we call it clusters. Okay, so okay, now we see. Okay, it's okay. You may take the break a bit later. Therefore, we come back a bit later. I need some time to discuss this. Okay, we see a bit more. Yeah. Okay. So therefore, the group A, I mean cluster A, cluster B, maybe something like this. Yeah. A will be someone who always answer 2, 1, 3, like this. Okay. So B will be always answer 6, 7, yeah, 5, yeah, 7, 6. Okay. Therefore, if you see you see within group A, different not much. Within B, different not much, quite similar. We can make it become 2 different clusters. Okay, but the grouping you don't know. You can see. Of course, finally you may do the grouping. Maybe here is considered high income. Maybe, yeah. Okay, they want good food, they want good atmosphere. Normally means high class restaurant in general, right? In general, okay. So this one maybe average, yeah, income, yeah, okay. So, okay. So now the objective, you want to identify the groups that maximize the ratio. Yeah, maximize. The between group variance. Yeah. Okay. Okay. Example. Let's say this one respondent always answer 3 and 2. You should know this respondent should put it into this category. Because you put it in this category, what happened? You put it into this category, therefore the variance in the B will be higher. If including okay, if you including two more, let's say these two respondent, you put it here. We know the variance will be high. You see? Okay. Because 2 and 3 differ quite a lot from 7 and 6. Okay. 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 So now we see, let's say, example like this. Yeah, 1, 2, 3, 2, 3. Therefore, the variance will be small. Yeah. This is formula, the function to compute the variance, yeah, of the sample will be small. You can see? Okay. But let's say including like this, yeah, 2, 3, 4, 5, 6. Yeah, like this. Therefore, the variance will be large. Can you see? The variance will be large. Okay. Can you see? 3.5. Therefore, not proper. Yeah. Okay. You want to maximize the ratio. Yeah. Maximize. What ratio? Okay, between group. Okay, between group variance and within. Okay, within group variance. Okay. So this 0.6 actually is within. You can see within group variance. 3.5 is also within group variance. Okay, means within group A and within group B. Okay, you want to maximize this ratio. So this value should be large. This value should be small. Only can maximize. Okay. Okay. So okay. So what we do if if no question. Okay. Okay, it's okay. We continue. Yeah. Okay. So if we end a bit late, then also let us start a bit late. Yeah, because I want to finish this part. Okay. So yeah. Okay. So you want to maximize this ratio. Therefore, the within group variance should be small. Example, let's say here 6. Can you see? You change to the number that's similar to 7 or 6. Therefore, the within group variance for the group B also will be smaller. Okay, can you see like this? Okay, yeah. So that's the within. But for the between means we do everything. Yeah. For the between meaning that we use everything. Yeah. Okay. Actually, it's not this. Actually, there's another formula to compute between group variance is a little bit. It's okay. Okay. But from here we know also the variance should be large because in the A, the X bar is small. X bar for A is small, but X bar for B is large. Therefore, the between group variance must be large. Okay. Yeah. So that's why. Okay. So that's what we are going to do. Of course, the software will do this for us. We just do the interpretation and make sure you know the meaning of this. Okay. So you want to maximize the ratio of this. So it should be large over small. Therefore, the video will be large. So, okay. So it's an example of the cluster analysis. You only have this construct. You don't know this yet. At the beginning, you don't know. Yeah. But you try to base on these few criteria, few construct to do the grouping, yeah, for your employee to see they supposed to belong to each group, high, medium, or low, like that. Okay. So okay. Okay. Any question? Yes. Okay. So if no, so now we take a break. We see you at 5:35. Yeah. Okay. 5:35. Yeah. 5:35.
Okay, see you, sir. Thank you.
Okay. 5:35. Yeah. 5:35.
Hey guys, the class is in the meeting now.
One more audit, yeah. ordinary least square method. We use this method to estimate the